Can you read number 10 for me?
In an accident, the distance it takes the car to come to rest is a meter. How long does it take for the car to come to rest, and what is the acceleration of the car? Using a seatbelt and airbag can add an extra meter to your stopping distance inside of the car. How does this affect the acceleration the occupant experiences?
All right, so we're saying that the car crumples, basically. So they're saying it takes a meter to come to rest. Car accidents are terrible because they're such fast changes. So what was the original speed? 20 meters per second?
Yeah.
And the car is going to come to rest. So the final velocity of the car is going to be 0. The initial velocity of the car is 20 meters per second. And in the first instance, we're saying that this all takes place over a displacement of 1 meter. That's how far the car travels while coming to rest. I believe I've captured all the information that's in this problem. Is there anything else that I've missed? So in the first instance, we're talking about the car coming to rest, and they want how long does it take the car to come to rest, and what is the acceleration experienced by the drivers, or I'm sorry, by the car. In the second one, the idea is that the car comes to rest in the meter, but you don't come to rest for another meter because you're moving inside the car. So the difference between the two parts of the problem is one's talking about the car coming to rest and the other one's talking about you coming to rest, and your supplementary restraint system giving you more distance to move. So here it's 2 meters. Final velocity is still 0, initial velocity is still 20 meters per second because you're a part of the car. And here it's 1 meter. Again, final velocity is 0, initial velocity is 20 meters per second because we're talking about the car. I'm going to make this direction the positive direction. So I'm going to make the direction of motion of the car positive. So I'm going to assign positive and negative to everything here. The displacement's positive, the initial velocity is positive, the displacement's positive, initial velocity is positive. They want the acceleration in time, so we're just looking for a relationship that will give us each of those. So the relationship I think that will work the best for acceleration is going to be v squared minus v naught squared equals 2a delta x. This has all 4 pieces of information in it. It doesn't have time in it. We don't know what the time is. It seems like the right way to go. Any question about why you chose that? All right. So that's going to be 0 minus 400 equals 2a times 1. That's everything, right? So my acceleration is going to be negative 200 meters per second squared. That's a lot. It would be difficult for you to survive without injuries if you stopped that suddenly. Yay. Was there anything in it?
They said they're giving me a third because I didn't put the right.
Oh well. Well, I'm sorry, but thank you for going down there anyways. So we're going to repeat the problem, but it's the exact same problem, but with 2 meters as a stopping distance. So v squared minus v naught squared equals 2a delta x. So this is if we add the extra meter for your restraint system. So this side will still be negative 400. That's not going to change. This will be 2a times 2, which means the acceleration is cut in half. Double the distance, reduce the acceleration. So that's, every time you can do that, that makes your car accident way more survivable. Now we're not actually done because I believe it wants how long it takes to stop as well, but we should interpret the negative sign here to indicate that it's against the direction of motion. On your test, read carefully for the words, what is the magnitude and direction of the acceleration? It is not uncommon that I would have the question written that way. I'm asking for you to be able to make sure you state both things, both what the size of the answer is and a sentence or a couple of words that explains the direction. Does everybody understand? Putting a negative sign or a positive sign may not be sufficient for that if you don't have enough information in the drawing or in a drawing for me to interpret what negative or positive means. So does everybody understand that if you're asked for the direction, be specific? So, I'm going to say to the left or against the direction of motion. Right? We don't need the picture anymore, but we do need to solve for the time. I'm going to use a relationship that does not have acceleration in it, because if I made a mistake solving for the acceleration, I don't want to repeat that mistake. So looking at the list there, I think I'm going to use delta x equals 1/2 v naught plus v times t. Any questions about that? Excellent. So delta x will be 1, and that equals 1/2 of 20 plus 0 times t. So it looks like t takes 1/10 of a second. This one's going to be a little different. I'll have 2 equals 1/2 times v naught plus v times t. So that's going to be, go ahead and put the 20 in there. 20 and 0. So again, this would be 0.2 seconds. On a test, only correct if the units are there. So if you don't give me the answer with the units, you won't be able to get full credit. Form it if that's what you would like. All right.
A drive is inclined in such a way that rolling objects accelerate downward at 0.5 meters per second. This driveway has seams 2 meters apart. You watch a ball roll from somewhere above the first seam, and it takes 0.5 seconds to travel between seams. How far above the first seam did the ball begin to roll?
All right, so it sounds like the ball started here. And the seams are 2 meters apart. And you see the ball here, but it's already moving. And I assume it rolls to here and is now moving faster. And how long did it take for it to go between the 2 seams?
0.5 seconds.
So the time it took was 0.5 seconds. All right. They're asking us for this distance. How far above the first seam did the ball begin? And at this point, the ball was released from rest. All right, so let's consider that in this problem, which is designed to be a little trickier. I see that there's like 2 parts to this problem. There's what happened before the first seam and what happened after we passed the first seam. You guys see that? I think this is 2 different time intervals. So I'm gonna talk about what happened in the second seam and the first seam. In the second seam, the ball has some initial velocity that is unknown and some final velocity that is unknown. But we do know some things about its motion here. Let's consider what we do know. It's accelerating at 0.5 meters per second squared. It takes 0.5 seconds to travel between the 2 seams, and the 2 seams are 2 meters apart. That's the information given to me about that portion of the ball's motion. Before that happened, though, the ball was released from rest. It will also accelerate at 0.5 meters per second squared. But I don't have any other information except I want that. Now, I can solve for anything I want that's left over here because I have 3 pieces of information. Is there anything in the ball's motion between the seams that could be used to help us figure out where the ball started? Yes, sir? how would I use the final velocity? You're saying I should find the final velocity here? Okay, well, how could that help us? Okay, so your plan will find something different than what I need, but I think we could use your plan to find what we are asked. If we do what you're saying and make this the final velocity here, then delta x isn't this, but would be all of this, right? That would still help us, right? Because we know that we could use that to figure out how far the ball started, so that plan works. There were two options here. This is option number one, and it works just fine. You could have also found the initial velocity and used that for the final velocity here, because the final velocity during this interval becomes the initial velocity for this interval. Either one works. So we're going to go with the plan that you've laid out, because it works just fine. Let's find the final velocity. I don't need to picture much anymore. So I'm going to use probably delta x equals vt minus 1/2 at squared. That good for you guys? So 2 meters equals v times 0.5 minus 1/2 times 0.5 times 0.5 squared. Well, let's see, 0.25, 0.25. I don't know what that is, 0.0625? So this will be 2.0625 equals 0.5 v. Is that right or wrong?
0.5 squared is 0.25.
So 1/2 times 1/2 times 1/2 squared is 0.25? I'm trying to get this.
0.25 squared.
Right, so it's 0.25 times 0.25, which has got to be 0.625 something or other, or 0.0625. I don't know which. Is it 0.0625? Okay, so I add that to both sides and I get 2 plus 0.0625. I'm just trying to do the arithmetic quick because I don't care about arithmetic. And so this is going to be, let's see, v is going to be 4.125. That's meters per second. All right, so now we got to repeat this problem, but to find delta x. Probably use a different relationship based on the fact that we have these 4 things. So I'm going with 2a delta x equals v squared minus v naught squared. This one I'm not going to be able to do in my head, sorry. Well, maybe. No, I don't think so. I don't think I can do 4.125 squared. Yeah, it's not going to happen. It's more than 16, that's all I got. .015 meters. So it seems to me that the actual answer to the question isn't 17. 17 is this distance. We wanted this distance, so I'll have to subtract 2. So the ball started 15 meters above where the seams are. I bet the seams are like the sidewalk, you know, rolls all the way down the driveway, then hits the first seam of the sidewalk and the second seam of the sidewalk. So you understood absolutely none of that before. Do you understand more of it now?
Yes, thank you.
Well, that's great. That's great. Is there another homework problem you guys would like me to discuss? Yes, ma'am.
Can you please go over how you got the acceleration time for number 2?
Sure. I don't know what number 2 is.
Number 2 says, oh, it relates to number 1.
Well, then we'll probably need to know a little bit about number 1.
In number 1, a marble rolls down a ramp from rest with an acceleration of 0.75 meters per second squared over a distance of 2 meters. And then it was asking how long it then in number 2 it says, in number 1, the marble was pushed up the 2-meter long ramp with a speed of 2 meters per second at the bottom. Would it make it all the way to the top? And then if not, where did it stop? And then if so, how fast was it at the top?
All right, so we need the acceleration that the marble experiences from the same ramp. So we need the answer, the acceleration from problem number 1. Did you find the acceleration from problem number 1?
Yes, but I'm not sure if it's right. I got 1.73 as the number for the velocity for number 1.
No, I need the acceleration.
Oh, the acceleration, sorry. Oh, it's 0.75 meters per second squared.
Okay, so the thing is, it's the same ramp. So because it's the same ramp, it'll have the same acceleration, which you said is 0.75 meters per second squared. So, and the ramp is 2 meters long. Is that right? And is this the one where it gave us the starting velocity and wants to know if it makes it to the top of the ramp?
Yeah.
What is that starting velocity?
2 meters per second.
2 meters per second?
Mm-hmm.
Okay. You have a couple choices about how you work this out. We don't know at the start of the problem if the ball makes it to the top of the ramp. So you can't assume then that it will make it to the top of the ramp. What you have to figure out is if it will make it to the top of the ramp. If it does, great. Then you can figure out how fast it's going when it makes it to 2 meters. If it doesn't, then you're supposed to figure out, well, how high up the ramp does it go? So what I would do is I would say we don't know this. Let's find that. We know that the maximum distance the ball can travel will be when its velocity is brought to rest. Starting at 2 meters per second, when it reaches a velocity of 0, that's the maximum displacement of the marble. We don't know how far that is. If it's more than 2, great. If it's less than 2, then that's the answer. So our job here is to figure out how far it can go, and then to decide how fast it's going at the top, if it is going all the way to the top. Acceleration is 0.75 meters per second squared. I'm going to make up the ramp the positive direction. So I'm going to assign positive to that value and negative to that value. And I'm looking for displacement. So we're going to see if this is 2 meters or more. Well, that would be 0 squared minus 2 squared equals 2 times negative 0.75 delta x. Negative 4, and let's see, 0.75 is 3/4, 2 times that is 6 2/3. Is that right? So that'll be 8/3. So let me check my math on that. Or did you just divide? I'm just trying to do the math in my head because you guys tend to be unsure of yourself. But what did you get? It's 4 divided by 1.5.
Yeah.
Which is 8/3. Which is 2 2/3. You guys are so unsure of yourselves. The negatives will cancel out, so you get 2 2/3, or 2.67 meters. Now, that tells me that it makes it to the top of the ramp. So, unfortunately for us, we have more work to do because it doesn't travel 2.67 meters. It leaves the ramp. So our job now is to figure out how fast it actually is going here, which means we do know the displacement. It's 2 meters. We can't assume the final velocity is 0. We need to find the final velocity. And this work was just enough to tell us that we know the marble will make it to the top of the ramp. So, bye-bye. And we'll do the rest of the problem this way. V squared minus V naught squared equals 2a delta x. So V squared minus 2 squared equals 2 times 0.75 times delta x, which is 2. That all look good to you? So v squared equals 4. Is that minus 3? 2 times 0.75 is 1.5 times 2 again will be 3. So v equals 1 meter per second. I had to take the square root there, so I'm going to say 1 meter per second up the ramp. All right. Not terrible. Any one of these would be perfectly legit. Substantially changes the answer knowing that it's not supposed to be 1,600 meters, it's supposed to be 160 meters. Now, I'm still happy to perform the problem as stated at 1,600 meters so you can figure out what you would have to do. Or I can perform the problem with the correction to 160 meters. It's your decision.
We'll go with 160 meters.
Okay. So the car is going to be slowing. We don't know the acceleration, but we know that it's going this way and that it will take 160 meters to come to rest. So velocity equals 0. Worst looking cars ever. What's the, there's other information given, like time and something else?
Yeah, 3 seconds.
All right, so 100 meters per second is really fast. I've never been in a car that fast because that's going to be well over 200 miles an hour. So that's a pretty unrealistic speed. You know, unless we're talking about some kind of race car or something. So I try to give, you know, a little bit of perspective on speeds. When you're like on the highway, you know, 20 meters per second is about 45 miles an hour, 30 meters, you know, a little more than double meters per second gives you miles per hour. So a couple things just to keep in mind. I'm going to make this way positive again. Be careful about direction. Time is 3 seconds. Acceleration unknown. Final velocity 0. Initial velocity 100 meters per second. I'm sorry, we don't know what the final velocity is. We're just told that it slows down over a time period of 3 seconds in a distance of 160 meters from 100 meters per second. So these are both positive, and we're looking for this and this. Pick one. Which one do you want to do first? It's your problem.
Acceleration.
All right, so I'm going to ignore final velocity to solve for acceleration. I'm going to use delta x equals 1/2 at squared plus v naught times t. I'll get 160 equals 1/2 of a times 3 squared plus 100 times 3. So 160 minus 300 is negative 140. And that's going to be half of 3 squared is 4.5a. So a is going to be, I don't know what that is, 140 divided by 4.5. Negative 31 point.
One repeated.
Okay, and that's good. Meters per second squared. That's a lot, but that's not unheard of for a vehicle. So we need to find the final velocity now. So I'm going to just kind of go with what we have and choose delta x equals 1/2 v plus v naught times t. Use that to find final velocity. So 160 equals 1/2 times v plus 100 times 3. Nothing magical here. I'm going to double this and get 320 to get rid of the 1/2 over 3, and that equals v plus 100. Is that good for you? So 320 divided by 3 is 167?
106.
106, and then 6 repeating?
Yeah.
So 7 meters per second. or 6.6 repeating, but this is good enough.
It is launched from the ground with an acceleration of 20 meters per second.
Okay, what was the acceleration? I missed that part.
20 meters per second.
Okay.
So for 1.5 seconds, and then the engine finishes, the rocket goes into free fall. What maximum height does the rocket reach, and what is the total time the rocket spends in the air from basic height to the ground?
Okay. This is an excellent problem. I like it. It's test worthy. All sorts of things. The rocket starts with initial velocity of 0, but an upwards acceleration of 20 meters per second squared. It's very messy. So I'll do better. There, so 20 meters per second squared. It accelerates upwards for 1.5 seconds, giving the rocket some final velocity that we don't know. But at this point, the rocket doesn't suddenly stop and fall to Earth. It's moving upwards now, and gravity takes over and pulls down with the acceleration of gravity of 9.8 meters per second squared. That's going to eventually give the rocket a velocity of 0. There'll be a displacement during this time as well, right? Displacement upwards. And then the rocket will, starting from rest, will fall all the way back to the ground. Everybody understand the dynamics of this problem? I believe there are 3 different time intervals that we have to observe. There's a time interval when the rocket is under power, the time interval where the rocket is coming to rest while moving upwards, and then a time interval that it takes for it to come all the way back to the ground. Now, we could skip some of these, except I'm pretty sure the problem asked for the maximum height attained by the rocket, doesn't it? If, in order to find the maximum height attained by the rocket, we need the time interval where the rocket comes to rest as part of our problem. So these 3 time intervals, and it also wants the total time it's in flight, right? So we need all 3 of these time intervals in order to figure out the problem. So let's start with this part of the problem first and work the 2 parts that are here. We'll need this velocity so we know how fast it's moving when the engine's shut off. And we're going to need delta x for that portion of the flight. So looking at what we have, we'll have, we'll call this time interval 1. This is when a rocket's under power. Delta x, v naught is 0, v final unknown, acceleration upwards at 20 meters per second squared. I'm going to make upwards positive, and time is 1.5 seconds. I need both of these values, so there's no specific order to go in here. I'm going to do delta x equals 1/2 times a times t squared plus v naught times t. This will give me delta x. 1.5 squared is 2.25, I think. Pretty sure, because it's 15 squared. And then 10 times that. So is that right? 2.25 is 1.5 squared, so it's 22.5 meters is the displacement of the rocket during the first time interval. Any question about where I came up with that? All right. Next, I'm going to use these things to figure out the final velocity of the rocket after the engine's shut off. So I'm looking at v equals a t plus v naught. So that's going to be 30 meters per second upwards. And that's time interval 1. That's what we've got for both of those. Any questions about that? All righty. This represents time interval 2. So in time interval 2, delta x is unknown. Initial velocity is 30 meters per second upwards. Final velocity is 0, and acceleration is negative 10 meters per second squared. We can use negative 10 instead of negative 9.8 when we're working any acceleration of gravity problem. And it's a lot easier to use 10 than 9.8. And time, we don't know time, but we're going to need both of those because we need total time of flight and we need to know how high the rocket goes. So I'm going to pick one to figure out. Let's figure out delta x first. That'll be v squared minus v naught squared equals 2a delta x. So 0 minus 30 squared equals 2 times negative 10 times delta x. 30 squared is 900, divided by 10 is 90, divided by 2 is 45. So I think it's 45 meters. You guys want to check my arithmetic on that? You should. You should. It's 30 squared divided by 20. Because either you've done this problem and you know the answer, or none of you did it. Because you would agree with me wholeheartedly. 45 meters? All right. It's no good if I'm the only one doing this. I can pass the test, right?
Good morning, pardon the interruption. For make the most accurate record you can of students who are absent. You can keep that on paper or on a file on your computer. And once EdConnect is back up, you can go back in and enter that data. We do not have an estimated time for EdConnect to come back up, but please keep accurate attendance as best you can. That way, once it comes back up, you can enter that data in EdConnect. Thank you.
All right, so who's missing from the back table? Who? Blake? And that's it. All right. There, accuracy confirmed. We good so far? 3 seconds and 45 meters. So the rocket is 67.5 meters from the ground. It can bring us to this problem here where the displacement is going to be 67.5 meters downward. The acceleration is still the acceleration due to gravity, and the initial velocity here is 0. So this time interval represents the rocket falling back to the ground. You guys ever made rockets before?
Yes.
Who's made water rockets before? It's kind of fun, little elementary school thing to do. Anybody use any other kind of rocket, like use the little Estes rockets? They're kind of fun. We've got some equipment. We should try it. It'll be a fun day. I'm going to make downwards positive for this interval. There's no reason not to. That means the acceleration downwards is 10 meters per second squared, and this velocity is 0. This is 65 meters, also downwards. I think all we need is the time, right? It doesn't ask how fast does the rocket hit the ground. So we're just looking for t. 67, I'm not going to do this one. I think because I'm going to run out of time. But I also don't think I can do this one in my head. It's 67.5 divided by 20, then you have to take the square root. 3 point what? 3.7. So you needed the total time of flight. So the total time of flight is 1.5 seconds plus 3 seconds plus 3.7 seconds. That's total time of flight. Maximum height attained by the rocket, 67.5 meters. I think that's the whole problem. I think those are the things you needed. This is perfectly acceptable test question. Did you notice I got to make you use almost every one of the motion equations, and you had to figure out what to use from one problem to the next? So I like it. Yes, sir.
Can you go with number 7?
I'd be happy to, but I don't know what number 7 is.
Do you want me to read it to you?
Yeah, just give me the first couple bars. I probably know it after that.
When a drive is inclined in such a way that rolling objects accelerate downward at 0.5.
I've got it. This is the one with the seams?
Yeah, seems.
Okay, all right.
2 meters apart.
All right.
It takes 0.5 seconds to travel between them.
All right, so there's 2 seams somewhere in this driveway. And they are 2 meters apart. My vision of this problem is that it's kind of like, if it's anything like my driveway, the driveway goes down for a while, then there's the sidewalk, and there's a seam on either side of the sidewalk, and then the drive continues to the street. That's kind of what I envisioned in this problem. Does that make sense to all of you? The ball was started up here at the top of the driveway, and at that moment it had an initial velocity of 0. The ball rolls down the driveway, but is accelerated at, I think it's at, you said 0.5 meters per second squared,
Yeah.
and makes it to this point traveling, I don't know, some speed. We don't know what this distance was. Now, we know that in the time, when it travels from one seam to the next seam, that distance is 2 meters. And we know the time it takes is half a second to get across the 2 seams. We're being asked to find where the ball started. Okay, that's the structure of the problem. I'm going to make down the ramp the positive direction. Fair enough? I see 2 intervals. I see the interval that takes place before the ball reaches the first seam, and I see the interval that takes place between the 2 seams. Do you guys see that as well? That's how I would break the problem up and see what information has been given. There's another interval. You could also consider a third interval, which would be the entire trip. So 3 different intervals. I'm just going to look at these 2, but we could look at all 3 if you'd like. I'm going to put this as interval 1 because it happened first. And this is interval 2, it happened second. Interval 1, we do not know delta x, but we know the initial velocity was 0. We don't know the final velocity, but the acceleration is 0.5 meters per second squared. We don't know time. Interval 2, we know that the displacement is 2 meters. We don't know the initial velocity, the final velocity, but the acceleration was 0.5 meters per second squared, and the time was 0.5 seconds. This is all the information that was given to us from the problem. Now, it seems to me like I can determine things for interval 2 because I have 3 pieces of information, and we need 3 pieces of information in order to solve a problem. But I don't think I can determine anything in interval 1 because I've only was given 2 pieces of information. The question is there something from interval 2 that we could use in interval 1? Yeah. What do you mean? There it is. We can solve for this initial velocity, which had to be how fast the ball is going when it makes it to the end of interval 1. This is a connected problem. These 2 parts are connected together. I think the part that's challenging is you having to figure out how they are connected. So I think that's how they are connected. So let's talk about interval 1, and let's see if we can get that initial velocity. So I need a relationship that has everything in it except for final velocity. That seems to be delta x equals 1/2 at squared plus v naught times t. That a good place to start? So 2 equals 1/2 times 0.25, not 0.25, 0.5 times 0.5 squared plus v naught times 0.5. Any questions yet? All right. 0.5 squared is 0.25, and half of 0.5 is 0.25, and 0.25 times 0.25 is 0.0625, I think, right? 25 squared plus, again, this is just 1/2 v naught, and this is 2. So I guess I will just subtract 0.0625 from both sides. Does that work for you guys? I don't want to do that. Then multiply by 2. I don't want to do that. It's a lot of work. Can you guys do it? mean, I can, I just don't want to. Yeah.
3.875.
V naught equals 3.875. Sounds great. We trust in your arithmetic. We all good? Excellent. So let's take this and put it there. Now we're going to do the part of the problem that happened before the first seam. So that looks like I'm going to use v squared minus v naught squared equals 2a delta x. So 3.875 squared minus 0 equals 2 times 0.5 times delta x. So delta x has got to be whatever 3.875 squared is. So something around 15, I assume. I'm just going to put 15 meters because I think that's pretty close. Now, we made downwards positive down the ramp. This 15 meters came out to be a positive number, suggesting that the ball traveled downwards 15 meters before reaching the first seam. And you should interpret this as being 15 meters away from the first seam. But I don't think that's really too much difficulty in putting together. First period did this problem as well, but they suggested we find the final velocity for this interval, not the initial velocity, and then use that to find the whole distance, and then subtract the 2 meters from that. So they did the problem a little differently. So if you want to see it done differently, that's fine. Same problem, get the same answer. There's several ways to approach this problem, but the question that you have to ask yourself is, if you don't know if the ball makes it to the top of the ramp, can you assume that it does? Like, could we assume it travels the 2 meters? Now, you can try that. You can put 2 meters for the displacement and see if you figure out what the velocity is, but be careful. If the ball doesn't make it to 2 meters, you are likely going to get some weird answers in your mathematics that might be difficult for you to interpret. And you guys generally have, in some cases, low confidence in your answers. What I would encourage you to do is go with the guarantees. There are some guaranteed things that you know to be true. For example, you know the initial velocity is 2 meters per second. You know that that's true. You know that the acceleration is 0.75 meters per second squared. You know that to be true. And you know that for the ball to come to rest, its final velocity is going to have to be 0. We don't know if that rest point is before the top of the meter or after the top of the meter. I'm sorry, meter. Before the top of the incline or after the top of the incline. So I don't think we can count on it. I think we could figure out if it makes it the 2 meters or not. Now, having done this problem before, I know that it makes it the 2 meters. But let's work the problem using this idea that maybe we didn't. I'm going to make up the ramp the positive direction, which makes the acceleration negative. And I'm going to use, let's see, I'm going to use everything but time so I can figure out displacement. So that's going to be 0 squared minus 2 squared equals 2 times negative 0.75 times delta x. We all good? I have a tendency to like fractions more than decimals. So 0.75 is 3/4. That makes this 3 halves. 2 squared is 4, so this is negative 4 times negative 2/3. And that equals delta x. So that's 8/3. So that's going to be delta x is 2 2/3, or 2.7 meters. The ball makes it to the top of the ramp. In fact, it makes it way past the top of the ramp. So our job now is more narrow. We need to figure out how fast the ball is going at the top of the ramp. So now we have to change the dynamics of the question, but at least we know the ball makes it to the top of the ramp. Does everybody understand why we had to do that part first? So I'm going to do a new problem where I say 2 meters is the displacement, and my initial velocity is 2 meters per second. My acceleration is still negative 3/4 meters per second squared, and I want the final velocity at the 2 meter mark. That all good? So I'm going to go with v squared minus 2 squared equals 2a delta x. This side looks to be -3. This side is -4. So v squared equals 1. V equals plus or minus 1 meter per second. I think it's the plus one. I think it's going up the ramp at that moment. So I will interpret the plus or minus as being up the ramp. What number problem is this?
9.
9?
Yeah.
We're just interested in finding the acceleration. So this one is relatively straightforward, and we're going to do the same problem twice. Once for rock and roller coaster, and once for an arrow being shot from a bow. I'll point out something important here. We don't use elastic to shoot people. It's important that you kind of be aware of that. These things that accelerate the cars are not springs. We would never use like a pinball launcher to launch people. It would likely kill them because the way the force is distributed from something that like elastic applies the maximum amount of force all at once right at the beginning, and the force gets smaller as the object moves. As humans go, we would not like that. It'd be like being hit in the back with a baseball bat the size of the roller coaster. So we use something different. You know, all of these use something that is more gentle. And it may not feel gentle. If you've ever been in any of the rides that do have a launch system, generally it's designed to ensure that it doesn't harm the humans. Now, Rock and Roller Coaster uses a similar system to what they use in the Hulk ride, and it's a pneumatic system. The Cheetah Hunt, and Velocicoaster and Hagrid's, they all use a launch system that uses electromagnetic system. The electromagnetic ones are nice because they are they work well under the conditions that Florida applies, because a lot of the stuff can be rained on and it's going to be fine. The pneumatic systems are a little touchy, which is why Hulk is often broken down, because it's a little bit older. All right, so this one, 80 meters per second from rest, and it does so the length of the arrow, which I didn't hear that part, 0.75 meters.
Yeah. Yes.
All right, so delta x is 12 meters. V naught is 0. V final is 30 meters per second. And we're interested in the acceleration. And we're going to compare that to an arrow being launched. 0.75 meters. Initial velocity 0. Final velocity 80 meters per second. There we go. So, yeah. Ant-Man being launched on an arrow, very unlikely. But let's go with it anyways. 30 squared minus 0 equals 2a times 12. Wow. Let's see, 80 squared minus 0 equals 2a times 0.75. This is just arithmetic, and I'm good at arithmetic. You guys are okay at arithmetic. Why don't you bang out those numbers? I don't feel like doing this one in my head. I mean, it's 900 divided by 24, and 6,400 divided by 1.5. But I think you guys have magical adding devices. And some of you should have done this for homework, so you probably have the answer. .5 meters per second squared. And the arrow? Yeah?
I got 4,256.6.
4,270 meters per second squared. Fatal for sure. It's okay for the arrow, not so great for humans. So yeah, we would not use that. You can't fire Ant-Man on an arrow like that. This, quite reasonable. Montu pulls more than this all the time, just on its turns. But it's very exhilarating to feel that kind of acceleration all at once. You feel it all the time, usually when you slam on your brakes, but usually that's a little different kind of exhilaration. So I probably should say that this was 4,300 meters per second squared, and this is 38 meters per second squared. On the AP1 exam, in the multiple choice, the responses that are listed there will often be using strict adherence to significant figures. So you should be prepared for that. Now, I really don't care that much about significant places. I do not grade on it. It's not a curricular point for us. You're supposed to have already learned how to do that, but I am not going to have a strict adherence to it. Do not dump the entire register of your calculator, though. You follow what I'm saying? What I am doing in front of you is the example I'm trying to set for what my expectation is. Is that good? Excellent. In the car accident, although the car takes 1 meter to stop, occupants in the car take 2 meters to stop. They get the 1 meter afforded them by the crumple zone of the car and another meter afforded them by the use of an airbag or seatbelt or supplemental restraint system. If you don't have one of those, you're stopped by the dash, so you probably take less distance to stop than the car does. Or you go through the windshield, in which case you take a very long distance to stop, but that leaves other problems, right? So the supplemental restraint system is designed to do 2 things, increase the amount of time it takes to stop and distance, and therefore decreasing the acceleration experienced by the occupant. A 20 meter per second car collision used to be 100% fatal. So 45 miles an hour used to be a fatal accident. Nowadays, with the kind of safety systems built into cars, most people find a 45 mile an hour accident to be survivable with injuries. Now, when I say a 45 mile an hour accident, we're talking about 45 miles an hour to 0 in the span of the accident. Most accidents aren't like that, they're offset, so the cars generally continue to move after the accident and slow down, usually because they're busted up or because they hit the brakes. So we're talking about a front end collision at an intersection. That's the kind of accident we're talking about here. That's a hard accident on any car. So delta X is going to be 1 meter. Initial velocity is 20 meters per second. Final velocity is 0. We are looking for the acceleration and the time. We're going to do this problem twice, once with 1 meter as our displacement and once with 2 meters as our displacement. I'm going to make this the positive direction. That makes these 2 values positive. All right, we don't need the picture anymore. This will help people in the back see a little bit clearer. I'm going to use, I think, v squared minus v naught squared equals 2a delta x, find the acceleration. And that will be 0 minus 20 squared equals 2a times 1. And just because we know we're doing this problem twice, there's no reason why we can't use the work we're doing now and do it a second time. Once for 2 meters, once for 1 meter. 20 squared is 400, divided by 2 is 200. That's an acceleration of negative 400 divided by 2. So 200 meters per second squared. And on this side, it'll be 400 divided by 4, so the acceleration is negative 100 meters per second squared. So doubling the distance halves the amount of acceleration. Big difference. Probably still going to be injured. That's 10 Gs, but at least, not 20 Gs, which is maybe not survivable. We got to repeat the problem for time. I'm going to use v equals at plus v naught. No, I'm not. Why would I do that? I'm supposed to be modeling good behavior. Good behavior means I use all the given information. So that puts me at delta x equals 1/2 v naught plus v times t. Good behavior. So 1 equals 1/2 20 plus 0 times t. And 2 equals 1/2 20 plus 0 times t. So 0.1 seconds. and 0.2 seconds. Doubling the distance gives you twice as much time to stop. Accidents happen fast. Sorry, everybody, this is problem number 5. Didn't record it, but I'll say that the final velocity in the first interval becomes the initial velocity in the second interval. Total distance 1,000 meters. Good enough.